Okay, so today we're going to talk about vectors. And when you use vectors, you need to include a header file right here. I'll show that to you. And once we have that, we can create instances of the vector class. It looks like that. It's called a template class. It's parametrized by a data type. So here we have a vector of integer v. And we could have, a vector of double, say w. So we have this parameter, which is a data type. And look at this. You can have a vector of double. I think this space may be required right there. So this should be, I'll make that a U. That looks good. I think that this is no good. Yeah, so the language is a little bit unpolished. This is the first language I believe, the first language to do these kind of things. But now this is common. These are called container classes. A vector is a type of container. It contains data items, all of the same type. And so when you create an instance of a container, you pass in this data type. And so what do they call these? You see this now, they added this feature to Java at a certain point. When C# was invented, it came out as part of the C# language right from the very beginning. And these are three big languages that are used widely in industry. So they're all using this generics. I think they call it generics. It's a generic container. A generic container is a container of any type. A vector of string and so on. And it's like an array. It's very similar to an array. Now this vector gets created and it's empty, but it's different from an array in that it has a flexible size. This container here, this v, this instance of the vector class, has a size of 0. And now these vector instances in this example, this instance here is referred to by the variable name v, that they come with these operations or properties or behaviors or functions that you can invoke on them. And you do that through this dot operator. So we have the vector v, this container is empty. So if we invoke its size function using this syntax, the size function returns a 0. So we can assert that right there. Let's take a look at that. And there it is, silence. I should say alt test pass, right? There we go. So we can add elements to v by using a function called pushback. So we can push back a 3, say. Now the size of v becomes 1. So it's like you can't do that with an array. The size of an array doesn't change. I mean, in a sense you could. You'd have to allocate an array as big as you will ever need and just use different lengths. That's one way of using arrays as flexible containers. Now, we pushed back this 3, so when we did this operation, v is going to look like this. It's going to be an array of size 3. When we create the v, you can think of it as being as looking like that, just a collection or a list with no items in it. We can push back another value. Now the size is 2, and the vector will look like this. It has 2 items in it, a 3 followed by a 7. So when we push back a value, it's added to the end of the vector. We'll just check our work by compiling and running the tests. Now it's also possible, well, you certainly would need to do this, to access the elements in the vector. So v of 0, if you look at it, you pull it out with this notation. This sort of retrieves the value that's stored in position 0. And these are position numbers. There's our position numbers assigned to these. So this first item here, this number 3, is the first item in the vector. We say it's at position 0. So we start the labeling process at 0. This would be position, 7 would be in position 1, and so on. So once we have a vector of values, say v here, you can pull out what's stored in it using this syntax, use these brackets, and with the index value, or the index, or the position number. Sometimes we say index. So when we pull out the value, or we just pull out a 3, we copy out the 3. Actually, in the machine as it's running, this will take the value, probably take the value out of RAM, the value 3, and copy it into a register, a CPU register. Maybe that happens here. Maybe, I'm not sure though. And if we reach in and look at the item in position 1, it should be a 7. Now, the item in position 2 is not defined. So we don't know what we're going to get there. Probably the best guess is a 0, but you don't know. You just don't know. And it does not give you a compiler error. Other languages, like Java or C#, you can't pass in an invalid index. See, the size of v is only 2. So, but here we're trying to access the third element in it. Well, there is no third element. Right? Index 2 is the third element. And so that's called a out of range error, or an out of. And these other languages like Java or C# will throw an exception. It will be like an out of range exception. But in C++, we don't have that ability. And maybe you can turn it on in recent versions of the language. It's possible you can turn it on, but I don't think it's turned on by default. So the behavior here is unknown. It's the unknown result. I mean, the odds are pretty small that there's going to be an 11 in that undefined position. But what I want to do is show you that it's possible to accidentally access that memory. See, the program runs well. The assertion, everything is okay. We don't get a memory exception. You know, if we did something like this, you know, we're going to get a memory exception. No, we didn't. Sorry, it's not big enough. Try a little more. That's that. Segmentation fault. There we go. A segment refers to a block of memory that we would be restricted to. Something like that. So the language lets us, it lets us make this kind of error, this logic error. It doesn't really help us much to find this error when it occurs, unlike other languages. So you've got a size function, you've got a pushback function, and you've got the ability to read values out of the vector, and you also have the ability to modify what's stored in the vector. So if we want to overwrite the 3 with a 10, we can do that. So we use the assignment operator, the familiar assignment operator, to change the value in V, to change the value at position 0 in V. You could do the same thing with position 1, so on. And that's about it. I mean, you can imagine, I mean, there's more functions. Okay, there's more functions to deal with, but these are all the functions you need in this class. Pushback, size, and you need the square brackets, which you already know how to do from working with arrays. So the only thing new we're learning today is just this new syntax, and that vectors have a flexible size, which is different than arrays. So all of the problems that, like this one, for instance, binary search, all of these problems involving arrays can be rewritten using vectors. Let's do that with this one here, just to see how straightforward it is. So binary search. So we want to read in, so instead of an array of int, it'll be a vector of int. I'll call it V instead of A. Okay. And now built into vectors is that size function. So we don't have to pass around the length of the array anymore, because we use that size function, v.size, to pull the size out of the vector. So we can just delete that. And k here, that's the number we're looking for. So we're getting this vector of integers that are an increasing or decreasing sequence. Well, increasing here. And a value k. We want to, the problem is to find out whether k is in V or not. Now, the way this parameter is written right here, we're making a copy of the vector when the function gets called. So that's very wasteful. What if the vector is large, like the size of 1,000,000 items? Then we're making a copy of a 1,000,000 item vector just to run the function. And when we return from the function, we discard the vector. We discard the copy. So what we want is a reference. I put that ampersand in there. Right between the data type and the variable name, this ampersand. That means this parameter V is a reference. That means no copy is made of the vector coming into the function. Did we talk about this already? We didn't. We talked about functions though, didn't we? I didn't cover this. I may have covered this in functions, but there's probably no way you would have remembered this. Or maybe I didn't cover it. So that's what's going on. This is actually very important. This is an issue that happens in all languages. It's not, sometimes in other languages, the languages are designed so you don't have to think about it as much. But this issue is present in all languages, all computer languages. When you pass a variable into a function, when you invoke a function and you pass data into it via a variable, okay, there's two things that could happen. The system could make a copy of the data and the function operates on the copy. Or the system just lets the variable refer to the original data without making a copy. So that second case is the case I'm illustrating here with that ampersand. This is, we call this a reference. So V is a reference to the vector, is a reference parameter. There's another typical keyword that's used here to tell the compiler a little bit more about what we want. Const. See, when the function runs, it's not going to modify the variable v. It's not going to modify the contents of the vector or its size. And so we can tell the compiler that fact by typing, using this keyword const in front of the data type. So this is an instruction to the compiler, or it's information to the compiler, that our function will not modify v. It'll only access the elements in v, call the functions that produce data from v but do not modify v in any way. So const is short for constant. So you can calling code can assume that that whatever v I pass into the function will not be modified when the function runs. Yeah.
So you're saying the ampersand and const go together, or like
they kind of go together. Because see, if we had this, then we're making a copy of v, but we can't change it. It doesn't make any sense. Why make a copy of a 1,000,000 item vector if we're just going to read from it anyway? It's very wasteful. But if we want to modify v, like change some of its values, then we'd have to do this. So the two things, they work together, but they're two different concerns. But in our case, this would be, this ampersand turns v into a reference parameter, and it keeps the system from wastefully making a copy of the vector. And the const over here is a conservative action to take, because if we accidentally modify v inside the function, the compiler will flag that as an error. So we'll be able to catch the bug. Also, usually when you're writing these functions, some other programmer or yourself, a month or two later, needs to call the function and use it. And when you see const there, oh, this function doesn't modify any data I pass into it. It's just for calculating something. It's just for returning information. And so it tells the programmer something. It describes more information about the function. So now we changed the name from A to V. So wherever I have an A there, I'll change it. And that's it. See, the rest of the algorithm is the same, isn't it? I just changed V. I mean, if I had left this at A up there, if I left it at A, none of this would change. Oh, there is something that needs to change in there. Can someone see what else needs to change in that code? Yeah. The length is no longer a piece of information that's provided separate from this container of integers. So we get the size out of the vector by calling its size function like that. Now let's create some test data. I think someone showed me this the other day. I'm going to leave it at A down here. This is a vector of int A. I think this is valid syntax in C++ 11. I think someone showed that to me the other day. And let me try it. So this should fail because it's an older version of this C++ language. It does not fail. It works. Oh, so this works. That's news to me. I thought I was going to have to set the version, the standard, to C++, was it C++ 11? Yeah. But it's not necessary, apparently. It's whatever the current version is here. I think it's 98. Does this give any information about it here? How to get the version out of the compiler? I don't think this is going to work. There's some way to do it. I don't know how to do it. So there we go. That's it for vectors. Not too bad, right? Finding the maximum value, I think we did that already with arrays. Appending onto appending integers here. So you've got a vector v. See, look at this function. It's not defined with const. My maximum is const because finding the maximum integer in a vector of integers doesn't require that we modify the vector. We just need to read from it. So we can declare that parameter as const. But in this case, if you read the description of what the function does, it modifies v, so we can't declare it as const. Because the compiler will see there's some instruction inside the function that modifies v, and that'll cause a compilation error. Yeah.
You said the ampersand means you're reading from the original or reading from a copy?
Reading from the original. So you almost always use an ampersand, almost always. For something like a vector, it's almost always an ampersand, almost always a reference. It's a reference parameter. So this function is, pass in some vector, and the function just appends these numbers, 0, 1, 2, so on, all the way up to n minus 1. Just appends those numbers onto the end of the vector. That's all it does, and then returns. So it's going to call the pushback function to do that. So if the function has a pushback in it, we can't declare v as const. Here's another example. Suppose we have this function, append vector. It has two arguments, a vector of int v, a vector of int w. Notice the w is const, but v is not const. That's because this function modifies v. It takes all of the elements from w and adds them to the back of v. So if v were to be these three items together in the container, and w were to be 11 and 3, like this, then the result, after you call the function, v would become this, this sequence here, 4, 2, 5, 11, 3. So that's how the problem defines the function. And you need to write test code for this too as well. Vector insertion. Define a function that takes a vector such as a vector like this, something with the values that are in order. So this is an increasing order, 3, 6, 7, and 12. And if you pass in the a number, 5, and the job of the function is to insert 5 into the sequence. So 5 would have to go into the second position. So you're going to modify V. How would you do that one? Well, the size of V has to grow by 1, right? So I gave you all the functions you need to know, size and pushback. So what do you think you're going to call? You call pushback, right? Call pushback once. And then you got an extra slot in the vector. Now you got to rearrange the items in the vector so that the result, is a sequence of integers that are increasing. So that's a nice exercise. Count occurrences, we did this for arrays, didn't we? Yeah, so this is all a repeat. So this is just practice. Are identical. Is A and B identical? Or are A and B identical? Now for vectors, we passed in the length of A and B. So we assumed that A and B had the same length. For arrays, for arrays. But for vectors, when we call the function like this, it's possible that A and B could have different lengths. So you want to check to see that A.size equals B.size. This is the first thing you want to check here. If the size of A is different from the size of B, then return false. And the unlucky function, that's pretty straightforward. Oh, this should be const, by the way. Made a mistake on that. See, it'll still work, but it's just sloppy programming. If I didn't leave const, because this is unlucky function will not modify V. So let's go ahead and declare that as const. That's good practice. You certainly want to do that when you go to interview for a job. You want to show that that organization that you're trying to get a job at, that you're a programmer that's attentive to details like that. And ordered vectors. Is V, this function returns a bool. Are the integers in V in a strictly increasing sequence? Return true if that's the case, otherwise false. So this sequence here is strictly increasing. So the function would return true for this sequence. This V, this vector would turn true. But this one is not strictly increasing because it's increasing. It's non-decreasing, but it has a repeat here. So it's not strictly increasing. It levels out at this point. And flatten, this one here is always confuses everybody. And but this one is not too bad. I'm going to show everybody how to do this one. Because I'm going to do that to avoid the confusion that, by the way, I'm taking this problem out. So next quarter when I teach this class, I'm not going to use this problem anymore. It's such an artificial problem anyway. It's just not that valuable to use. But it's assigned, and we need to do it. So let's look at flatten. Let's implement flatten here. So we have a vector of size, we have an array with 100 rows and 200 columns. And your job is to implement the function so that it creates a vector that contains these items, turned into a simple list. So you put in the first row, followed by the second row, followed by the third row, like that. And I think I gave test code there. Here's the test code. And I added this in the middle of the quarter. So we need to use this test code specifically. We create a two-dimensional array filled only with zeros. And we modify one item in that two-dimensional array. In the second row, row one is the second row. In the second row, in the first column, we'll put a 3. And other than that, everything else remains a 0. And then we call the function flatten right here, and we get its return result, v, the vector v. And then we check the size of v should be 100 times 200, right? Since we flattened it out. It's an array of 100 by 200, 100 rows and 200 columns. That's going to be, what is that? 20,000 cells. And then in the 201st cell, or the 201st position, which is position 200, because remember, counting starts at 0. This is confusing, right? So if you go from 0 to 199, those should all be zeros. But position 200 should have the 3 in it. Okay. Took me a little while to come up with this test code, by the way. I got it wrong when I first did it. All right. So let's flatten it out now. Let's see how this runs. Now this function does nothing. So let's test the test code. The test code should fail here. And it does. Now let's implement the function. So normally we process it, a row at a time. So for each row, we're going to scan through the columns and append each item from each column in the given row onto V. So there's 100 rows. Do you want me to do this? Or do you want to figure this out on your own? There's a lot of problems. There's 9 problems. I'll show this to you all the way here. Show this to you all the way. So not R, but C. C is less than 200. Okay, so the first loop it sets R to 0, and then the inside stuff runs, right? And then it sets R to 1, then the inside stuff runs. Think of it like that. So what's the inside stuff? So for R0, for the first row, R0, we're going to let C range from 0 to 199. And for each of those positions in the particular row we're at, we're going to just copy what's there in that cell and append it or paste it, push it back onto V. And we need a V to do that. So we'll need to create a V. But first we'll just write that in there. Push back A, row, column. So we need a V to actually operate on. Let's create that. There's an empty vector V. And this is where we add to the vector. You see how R, you can think of this in this inner loop, from the perspective of the inner loop, R is fixed. The row is fixed. You know, it's not until we exit the loop and we go, the outer loop takes charge and increments R. But just if you're looking just at the inner loop that I have highlighted there, R is fixed. And so C is, we're going to let C range from 0 to 200. And for values 0 to 199, we execute the pushback. When C hits 200, we do not call pushback. We finish the inner loop at that point. Then we can advance R. One last thing we got to do. What do we have to do? Yeah, return V. See, flatten returns the vector. It creates the vector and returns it. Yeah, I'm not sure it's such a good design here, because it looks like copies are being made of this vector. So probably a better design for this function, I've got to tell you. I don't want to get too distracted here, but a better design would be this. Yeah, so we pass in this A, we pass in a non-const reference to the vector. So we just fill in this empty vector that gets passed into us. Because I think with this code here, with this code down here, see, we create a vector V right there. And then we add 20,000 items to it. And then we return it. But when we return it, what do? The V is then copied into this V. So we're going to create a new V, and then we do this copy operation. It's going to be this long copy operation where we have to copy over 20,000 items. Unless the compiler is optimizing and can figure out that a copy is not needed. Is the compiler smart enough to know a copy is not needed there? I don't know. I don't know enough about how the compiler works to know if the way I have the problem written is inefficient or not. I don't know enough about the language. So, but I know that issue is there. So this would be a better solution for me, rather than researching that. I'd had to think pretty deeply about that. We could do that. It's probably a good idea to do that. But this would certainly solve the problem right here, is to, instead of returning the vector, pass it in as a reference. Create the empty one outside the code, and then pass it into the function. So that is kind of like a little tangent there. And there we have it, right there. Did we test this? I think we did. We'll try it again here. Looks good. So that's flattened. Like I said, I'm going to remove that in the future. I am lost. So this vectors assignment is due next week. The searching assignment is due this week. And we covered this already, right? We talked about this business. This is not too bad, right? 3 problems. And problems 2 and 3 are practically the same thing. It's just trivial to go from exercise 3 and do exercise 2 to exercise 3. They're really essentially the same problem. So, and search is pretty straightforward. So this exercise is not a big deal. but it's important, of course. The binary search is in there, right? So binary search is an algorithm that you should have, I'll say, committed to memory. It's better to commit the idea to memory and then kind of produce the algorithm in the exam from that understanding of the concepts. That's a good way to do it. But you might miss a detail or two that way. So binary search. And then we have one last topic to cover, classes. And we'll do this next time. So this will be challenge classes. Any questions? Anything you want to talk about? Okay, that's it then.